Let's talk about the kidney. Let's talk about the nephron, and more specifically, let's talk about diuretics. Okay, these are drugs that are very commonly prescribed, and they are used to increase urine output. So they're used to increase the volume of urine that your body produces by filtering the urine out from your blood. Okay, so the first thing I'm going to do is, in our discussion of diuretics, I'm going to show you how to draw the nephron, because you'll see this will come in handy when we're talking about the different types of diuretics and the places within the nephron where they act. So the first structure that we're going to draw is called the Bowman's capsule. This is the part where blood from the glomerulus is filtered and becomes part of the forming urine. So from the Bowman's capsule, we're going to go to this structure here, which is called the proximal convoluted tubule. Moving right along, we're going to move to the loop of Henle. There is a thick part and a thin part, as well as a descending and ascending loop of Henle. Okay, so here we have our thin descending limb. Here we have our thick, thin ascending limb. And here is the thick ascending limb. Okay? Thin descending limb, thin ascending limb, thick ascending limb. Okay, these are both abbreviated by TAL, but if you draw the nephron correctly, you won't be confused because this part will be thicker. Okay? Then, because we have to be symmetrical, we're going to have a distal convoluted tubule right here, and then the forming urine will pass into the collecting duct. Collecting duct. Okay, we'll just call it that. That is the last significant structure that we're going to discuss for today's discussion. Okay, and I'm just going to label again here. This U-shaped structure is the loop of Henle. Okay. Okay, now that we've drawn the nephron, I would encourage you now to take a minute, pause the video, and draw it for yourself, okay? Because as we move on with the rest of the video, you'll be able to label on your diagram of the nephron exactly where these different classes of diuretic drugs act. Now, before we start talking about their mechanism of action, we need to first discuss which types of classes of diuretic drugs are used. Okay? So the way that I like to remember these classes is to use the acronym COLTA. C-O-L-T-A-A. COLTA. Okay? The first one, the C, stands for carbonic anhydrase inhibitors. The second one is osmotic diuretics. The third one, L, is loop diuretics. These are usually the most common. Then we have thiazide diuretics. Then the last two A's are aldosterone and ADH, antidiuretic hormone antagonists. So take a minute to write this down as well, and just appreciate that these are the different classes of diuretics that are commonly prescribed. Okay? COLTA, C-O-L-T-A-A. Now, conveniently, we have these listed in the order from proximal to distal of the nephron where these drugs act. Okay, so this is going to help us in labeling our diagram of the nephron and demonstrating precisely where these drugs are active in the body. We've listed the different classes of diuretics that are commonly used. We can now start to go ahead and return to our diagram of the nephron. And we can label the different parts of the nephron to indicate where the specific classes of diuretics are active. Okay? So the first class of drugs, if you remember from the acronym COLTA, is carbonic anhydrase inhibitors. And these are active here in the proximal nephron, okay? And I'm putting a dot here on the proximal convoluted tubule to indicate that this is the site of action by carbonic anhydrase inhibitors, okay? The way that these drugs work is by inhibiting carbonic anhydrase, which is an enzyme that is responsible for the production of carbonic acid, okay? When carbonic anhydrase is inhibited, when its activity is suppressed, that results in the accumulation of sodium bicarbonate in the forming urine within the proximal convoluted tubule. Okay, it results in the suppressed resorption or decreased resorption of sodium bicarbonate in the proximal convoluted tubule, and that results in increased diuresis because you're creating an osmotic gradient, an osmotic effect that's pulling more water into the tubules of the nephron. Okay? One common drug within this class is called acetazolamide. Acetazolamide. That is a common carbonic anhydrase inhibitor. The next class of diuretic drugs on our list is osmotic diuretics. And I'm going to indicate osmotic diuretics right here at our loop of Henle. These drugs are actually active all throughout the nephron, but they seem to be most active in the loop of Henle. Okay? So the way that these work, I'm just going to write osmotic. The way that these drugs work is by diffusing into the lumen of the nephron, as in the lumen of the loop of Henle, and in doing so, they create an osmotic effect. Their concentration is larger within the loop of Henle than it is in the blood, and because of that, it pulls water from the blood into the lumen of the loop of Henle. Okay, and one of the common drugs associated with osmotic diuretics is mannitol. Okay. These diuretics are very powerful and very strong. Okay? Osmotic diuretics, they're active throughout the nephron, specifically in the loop of Henle, and they work by inducing an osmotic effect that pulls water from the blood into the lumen of the nephron. Let's now move on to loop diuretics, which is the third class within our acronym COLTA. We have the L now for loop, and I'm going to indicate that loop diuretics are most active here in the thick segment of the ascending limb in the loop of Henle. Okay, and I'm going to draw a line just so that we are clear. Okay, so this is where loop diuretics are most active. Loop diuretics work by inhibiting sodium-potassium chloride symporter. This is known as NKCC. And because of that, more sodium builds up on the inside of the lumen of the thick ascending limb of the nephron. Okay, and that again results in an osmotic effect of water being drawn to the compartment of the nephron that contains more sodium. Okay? And one of the most common loop diuretics is furosemide. Otherwise known as Lasix. Very, very common loop diuretic. And I'm just going to make a quick correction here that this is furosemide with an E in the middle instead of an A. Furosemide. That brings us now to our discussion of thiazide diuretics, thiazides, which are active here in the distal convoluted tubule. Thiazide diuretics work similar to loop diuretics in the sense that they block the luminal side of a transporter protein. This transporter is called the NCC. It is the sodium chloride transporter. And by blocking this transporter, thiazide diuretics are again able to induce an osmotic gradient such that there is more sodium chloride in the lumen of the nephron than there is in the blood. And this results in the osmotic effect of water being drawn into the lumen of the distal convoluted tubule. A common thiazide diuretic would be hydrochlorothiazide, abbreviated as HCTZ. This is the classic example of a thiazide diuretic. Let's discuss the class of diuretics known as aldosterone antagonists. And these are active here in the collecting tubule. Okay, so this upper half here is the collecting tubule. This lower half here is the collecting duct. Okay, it's just anatomical semantics, but there you go. So here in the collecting tubule, we have our aldosterone antagonists. Aldosterone is a hormone that in the kidney is responsible for retaining, reabsorbing sodium and excreting or getting rid of potassium. So the reason why aldosterone antagonists are known as potassium-sparing diuretics is because they inhibit the aldosterone receptor, thereby reducing the amount of potassium that is excreted from the kidney. Okay? And in doing so as well, it also holds on to sodium in the collecting tubule. Okay? And because sodium is not being resorbed back into the blood, instead it's hanging out in the collecting tubule, this causes water again to be to diffuse over from the blood into the nephron, okay, into the forming urine. So one common type of aldosterone antagonist is called spironolactone. And this is known as a potassium-sparing diuretic. Last but not least, let us discuss ADH antagonists, antidiuretic hormone antagonists. These are active antagonists. These are active in the collecting duct. They are the last and final defense as we move distally through the nephron, okay? Now, normally ADH is a hormone that's responsible for recruiting aquaporins, as in water-transporting enzymes, into the luminal side of the collecting duct. And what that does is it tries to absorb water, reabsorb water back from the forming urine and into the blood. Now, when we antagonize ADH, as in when we inhibit the activity of ADH, we are not allowing for the recruitment of those aquaporins onto the luminal side of the nephron. Okay, and what that happens, and what happens as a result is that water tends to be more excreted. Water tends to remain in the collecting duct as opposed to being reabsorbed back into the bloodstream. Okay, so one common ADH antagonist that has been used for years now is called demeclocycline. Demeclocycline. Okay, but it's being quickly replaced by a new type of drugs class called vaptins. Vaptins. Okay, so it used to be demeclocycline and also lithium. Now those drugs are being replaced by vaptins as ADH antagonists. Okay, so there you have it. These are the 6 major classes of diuretics, and I hope this video was helpful.